Hello everyone, we're looking at circle theorems. I'm your tutor, Mr. Lennon. Now, for this question, an exam type question, we are given certain information that we want to pay close attention to. First of all, we're told that the diagram or the circle is not drawn to scale, which means that you will not use your measuring devices to determine what the angles are. However, you'll use properties that you would have learned, or facts, angle facts you'd have learned, theorems, to determine what the angles are. So, first point is that line ACQ is a secant, in which the line segment AC is a diameter. Observe the diagram and compare what you're given. Here, it says line ACQ. So we look at the line, we're going to start from endpoint A, go straight down to or up to C, and right along that line to the endpoint Q. Why a secant? Because that straight line actually passed through the circle. Now, line segment AC is a diameter we're told, so we're looking at endpoint A, and we'll stop at C. So that part of the secant from A to C, we're told is a diameter. You know what a diameter is. Simply a chord with endpoints on the circumference. That's definition for a chord, a straight line with endpoints on the circumference. So A and C are on the circumference, but it passes through the center of the circle. So even though we're not given a dot indicating it's a center with a label, we know it's a diameter because we are told so. So sometimes we may get a dot in the center and told that it's a diameter. Next point, line PDQ is a tangent with the point of tangency D. So line, we're going to go from P, endpoint P, to D, straight down to Q. That's line PDQ. Now D is on the circumference. D is the point where the tangent touches the circumference. So it's just a touch. It doesn't pass through it. So that contact, that point of contact, is what we refer to as the point of tangency. If it passes through it, then we will say it's a secant. But in this case, it's not a secant because it just touched the surface of the circle or the circumference. The next point is that we have a polygon ABCD with its 4 vertices on the circumference. So here we have a polygon. Now poly means many, and gon refers to side, right? So a shape with many sides. This shape A, going from point A to point B to C to D. So let's go from A, that's one straight line. Then we're going to go from B now to C, another straight line. Then from C to D, that's another straight line. Well, we want to go back to A, where we started from, to close the shape. For it to be a polygon, the shape must be enclosed by 3 or more straight lines. Yes, 3 or more. So the first polygon we know of is a triangle. 3 straight lines enclosing that shape. The next is a 4-sided shape. We call that quadrilateral because there are many types of quadrilaterals. We have rectangle, we have square, we have rhombus, we have kite, parallelograms, etc. So any 4-sided shape, we refer to it as a quadrilateral in general, but there are many types of quadrilaterals. So what is special about this quadrilateral is that all of its 4 vertices, in other words, where the 2 straight lines meet at a point, a vertex is formed. V-E-R-T-E-X. V-E-R-T-E-X. So D is a vertex because we have 2 straight lines that meet at a point called D, 2 straight lines meeting at a point called C, 2 straight lines meeting at a point called B. So these are vertices, plural, vertex singular. Now let's see what we were required to do. So these are the requirements. Part A. What is the name of the polygon with sides A, B, C, D? Now, as mentioned earlier, the polygon here is a four-sided shape or figure. So it's a quadrilateral. But because the four vertices of this quadrilateral are found on the circumference, we call it that's correct, a cyclic quadrilateral. So for 1 mark, let's enter that information. So if you got that, you're correct. Now we're told that PDE, in fact, angle PDE is 65 degrees. That's the measure of the angle. When two straight lines meet at a point, an angle is formed. So we're talking about line PD meets line DA, forming the angle in the middle that we refer to as angle D. So angle PDA is what we're referring to as angle D here. So PDA, so we have to ensure we understand which angle we're looking for. So we're going to go from P, so this is the point P, we're going to go down straight to D, that's where we stop for the first line, and then we're going to go down to A. So angle PDA, we're talking about going from P to D, and we're going to turn at D, and that's where the angle, we turn at an angle, right? So this is the angle we're looking for. These two straight lines, PD and DA. When I say line, we're talking about line segments, because we cannot really draw a line. A line goes infinitely in both directions. So these are just portions of a line we call line segments. But we just say line, keep it short. Line PD, we're going to connect it with line DA and tie them together, and that's where we refer to as the angle. So we're going to go from here, there to there. And we're told that it's 65 degrees. So we just want to enter that information to help us. When we see something like this little hat symbol here, it means angle. So we say angle ACD. However, we can also use this symbol to mean angle as well. So this is actually saying the same thing as this. They're both saying the same thing. Angle ACD. Or instead of using the hat symbol or this angle symbol, we can actually use the word angle itself and put angle ACD. They all mean the same thing. It says angle ACD, so we're going to go from A, point A, but we need to get to C. So which direction are we going to go? Well, here is C, so we're going to travel along this line in a straight path. So from A to C, and we need to get to D. How are we going to get to D? We're going to turn along this line, straight path, right to D. So it's going to be this line, AC, and this line, CD, that they're asking for. It's this line, AC, and this line, CD, that will form the angle at C. So we're connecting these two lines, this line and this line. So we're going to draw a little curve there to indicate. So we're connecting these two lines, and this is what we want to find. We want to find out what angle this should be. Now, do we know any theorems that could help us? Well, we do not have parallel lines, so we would not use angle facts involving the parallel lines, because we do not have any parallel lines. In fact, we're not told so. So what we will do is to see if we can use circle theorems to help us. When we look at this angle here, what do we know about these two lines that actually form angle mark 65 degrees? Well, this is a tangent. PD is a part of a tangent. In fact, it's a tangent itself. And line DA or AD is a chord. And we know that an angle between a tangent and a chord is equal to the angle in the alternate segment. So the angle that this chord has standing on it, not in this segment, because you know the chord separates the circle into two segments. So this chord AD that is involved with this tangent separates the circle into two segments. This would be the minor segment, this area or region between the chord AD and an arc AD. This will be our minor segment. The area over here between this chord AD or DA and this major arc, the region here between both of them, the arc AD or DA, along the circumference, and the chord that region is the major segment. So this is one segment, and this will be the opposite or alternate segment. So the angle between the tangent and the chord AD, or the chord DA, is equal, this 65 degrees is equal to the angle that is found in this alternate segment. Not this segment that the angle is found in, but the alternate or opposite segment. Yes, the angle in this segment will be equal to this one. So it will be equal to which angle? This angle here, because only this angle is standing with both legs on chord AD. So if you notice that for this angle here, we have this first line, all right, our leg at point D, and this other leg on point A. And this angle is at the circumference. So the angle at the circumference, standing on the chord, is equal to the angle between that same chord and the tangent. Okay, and they are in opposite segments. So this one is in the minor segment, this angle is in the minor segment, and this angle here is in the major segment. And in fact, we refer to this as the alternate segment theorem, rather than using all those words. Rather than saying the angle between the tangent and the chord is equal to the angle in the alternate segment, we just simply say the alternate segment theorem. So we can say angle ACD, again, going from A to C to D, which is this one, is equal to angle PDA, which we're given here, which is equal to 65 degrees. And what's the reason for that? Let's put it in alternate segment theorem. And that is just for short of saying angle between a tangent and a chord is equal to the angle in the alternate segment standing on that chord, same chord. Okay, so that's for 1 mark. If you got that, then you're correct. Absolutely correct. Let's look at point C, part C. Angle ADC. So we need to identify where ADC is. Let's identify where ADC is. We're going to go from A straight on a line to endpoint D, and then we're going to change direction starting from endpoint D straight along to C. So we're going to go from A, look for where D is. Okay, once we find D, we're going to go on a straight path towards D. So that's line AD. And then we're going to change direction by looking where C is. Look at where C is and go on a straight path towards C. So we started at A towards D. I will make a turn right here. And then we go straight down to C. So this will be the angle that we're looking for right here. So let's insert that so we don't make a mistake. So this is the angle we're talking about right here. Right? This symbol should just show us that we're connecting which two lines we're talking about that meet to form the angle. So what angle is this right here? What angle is created by AD, line AD, and line DC? How can we find this angle? Well, do you notice that this angle, which is going to refer to it as angle D since it's the middle letter, right? You can have many different angle Ds, right? In fact, this one is angle D as well, PDA. D is in the middle, just as D is in the middle for ADC. But which angle D we're referring to? The one that involves vertex A and vertex C. Going from A to D to C. So they're looking at this angle. This angle, in fact, we recognize is doing what? Both legs are actually standing on the diameter AC. So if you look at the line AD, which is this line here, going from A to D, all right, is a leg of angle D, and it's standing on the diameter for one endpoint of the diameter. And if you look at line DC as well, let's go from D to C. Right? C is on the diameter, the other endpoint of the diameter. So the diameter starts from A and ends at C. So we're going from A right towards C. Those are the two endpoints, A to C. And A to C is a diameter. But the angle is right here. Angle ADC has both legs on the endpoints of the diameter. So we can say angle D is standing on the diameter at the circumference. So rather than saying this, we have a better way of expressing this. But the point though is that any angle that is at the circumference standing on the diameter will always measure 90 degrees. Okay, let me go over that again. Any angle that is at the circumference, if you notice that the angle formed here by these two lines, this line and this line, is actually at the vertex of it is actually at the circumference. So any angle at the circumference that is standing on the diameter is actually measured 90 degrees. So what I'm going to do, I'm going to change the shape of this line, the symbol that I used there, because when it's 90 degrees, we tend to put a square. So we say angle ADC is equal to 90 degrees. And a faster way of saying this, that the angle at the circumference standing on the diameter is 90 degrees. Faster way of saying it is just simply writing angle in a semicircle is equal to 90 degrees. But we actually have that the angle is equal to 90 degrees already. So do we have to put equal 90 degrees? No, because we're indicating why we're putting 90 degrees, because it's an angle in a semicircle. But if you're more comfortable putting equal 90 degrees here, that will be absolutely fine, but you get your full mark still. And perhaps writing angle in a semicircle equal 90 degrees will help you to remember it faster. So you can put that, no problem. So this angle again, standing on the diameter at the circumference, is 90 degrees. Remember that a diameter separates the circle into two semicircles. So that's the reason why we can say that this angle here is actually in or within a semicircle. Now let's look at the next angle, angle DAC. So again, we're going to use the same principle. We're going to go from the vertex D or point D to A, a straight line DA. So we're going to go from this point here, from D, straight along this line to A. Then we're going to actually change direction, identify where we're going. We're going to what now? We're going to from A to C. And here we C. So we are at A. Let's go again, D to A. And we're going to turn along this line in order for us to get to C. Remember, you must go in a straight line. So from D to A in a straight line, from A to C in a straight line. And so we're looking at these two lines, this line and this line, that actually form the angle at A, at the circumference there. So this angle here is what we are trying to find. I did say that this angle here is 65 degrees. Why that's the case, you can always rewind and play this over. Okay, so our focus now should be at angle DAC. So we're going to go from D to A to C. Now what angle is this? What angle is this? Formed by line AD or DA and line AC or CA. It doesn't matter which direction, right? We read it from C to A or A to C is the same line. So the angles formed by DA and AC is right here. But what angle is that? Do you notice that if we consider triangle ADC or ACD, that this will be the third angle of a triangle and the only one that's unknown? So if you look at this triangle ACD, remember to go back at A to enclose it. We have two angles already and we need to find the third one. So if I were to sketch this, this is known, this is known. I want to find this one. What must we do? Well, we simply take 180 degrees and we'll subtract the other two angles. We can add them up and subtract that sum from 180. So 90 plus 65 degrees. And that will give us our answer. So we put 180 degrees minus, and we find the sum of 90 plus 65. 5 plus 0, that would be 5. And let's add numbers in the tens column. 6 plus 9, that's 15. So that's 155. What we could have done, subtract 10 from this, add it to this, give you 100, and 100 plus 55, since we took 10 from this to make this 100, 155. A lot fast way of doing it. When we subtract 155 from 180, all right, so we can probably carry this to 160. So 180 minus 160, that's what? That's 20. And remember, we really didn't start from 160, but 155 in our counting. We need to add that 5 to the 20, get 25. Or we can just simply go ahead and use our calculator and subtract 155. All right, subtract 1 from the 8, leave 7. Carry that 1 by the 0, so we have to think of this as 10. Because borrowing 1 from 8 tens would be a 10. So 5 from 10 would be 5, and 5 from 7 will be 2. 1 from 1 is 0, so that's 25. So this is 25 degrees. But what's the reason for adding these two and subtracting from 180 again? Because we have the sum of angles in a triangle actually add up to 180 degrees. So what we put here, sum of angles in a triangle. All right, you can put equal to 180 degrees if you want to, but this is the reason given here why we're involved in the 180, why we add these two and subtract from 180. So if you have that, then that's a full mark. Let's now turn our attention to part E, QDC, angle QDC. So we're going to go from Q to D, and then from D to C. From Q to D, where is Q? So it's going to be part of this tangent. So let's look at Q right here, and we're going to go where? So we have Q here. Now we're going to go to point D. So we're going to go along this tangent line to D. And then we're going to go down to where? C. So we're going to go right. So we get right here at D. And we're going to go along this line straight down to C. So Q to D. So involve this line here from Q to D. And we're going to turn off from D straight along that line that carries us to C. So looking at this line as well. So we're looking at line QD, or line segment QD, and line segment DC. So that's the angle we're looking at. The angle that connects the two lines, D, line segment DQ, and DC we're talking about. So what is this angle? Remember, we were supposed to enter this value here, right? We said that this angle is going to be 25, so let's enter that, 25 degrees. Keep forgetting to put it in. Very important to put it in so it can actually help you to identify the other angles. If you notice that this line here, line QD, is actually part of a tangent, or it's a tangent itself. And this line DC is a chord. So it's the angle between what? This angle here, this angle right here, is the angle between a tangent and a chord. And so it's equal to the angle in not this segment here. Because remember, this chord and this little piece of arc here creates a segment. In fact, the entire circle can be divided into two parts by this chord here. So if you imagine you have a pizza and you cut it along C right down to D, along this line here, then this will be one part of the pizza called the minor segment, and this bigger piece we'll call the major segment. Now this angle is between what? This angle is formed as part of, not completely, but part of the minor segment, right? Because the angle can be only formed by two straight lines. But even though we have a curve here involved in the arc, which is a part of the circumference, arc DC or CD, and the chord, we call it a minor segment. So this angle is formed in the minor segment, but it's equal to the angle formed in the major segment by the same chord that divides the circle into the minor and major. Now, which angle is in the major segment? That is standing on this said chord, the divider. Well, this angle here, this angle DAC. this angle DAC. So this angle DAC with its legs are standing on this chord DC. Okay, notice that this angle here, this leg is on endpoint C, and this leg is on endpoint D. So the two endpoints going from D to C is the chord we're talking about. So this angle between the tangent and this chord DC is equal to the angle formed with its legs on DC in the alternate segment or opposite segment to this one. Opposite segment to where the angle here is. So this angle here, right here, in other words, QDC is equivalent to this one in the alternate segment of 25 degrees. So angle QDC is 25 degrees, or we can say it's equal to DAC. It's equal to angle DAC, which is equal to 25 degrees. And why did I connect these two angles together, angle QDC and DAC? Because they're part of the alternate segment theorem. Angle between the tangent and a chord equals to the angle in the alternate segment. So again, this is alternate segment theorem. Okay, now, is this really true? Of course, we could have looked at it from a different standpoint. We could have looked at it from a different standpoint. Are you seeing another way we could have actually gotten that angle? You may share that in the comments and state how you got that angle. Did you use the same principle, the same theorem that I used? Well, let's look at how we could have gotten it differently. I'm going to just do a quick sketch here. So here we have the circumference, part of the circumference. We have point D here, and we have tangent along that line there. So that's D. This is Q. Here we have one angle here, one leg here of part of the angle DADC. So here we have A, D, and we have C here. This angle here is 90 degrees. All right, this angle here is 65. So if you notice, this line PDQ is a straight line, correct? I mean, it doesn't look like a straight line, but it's just a sketch. It's a straight line that we have there, right? Line PDQ is a straight line. We have part of it which is 65. All right, an angle formed on it. The part of it which is 65. This part is 90. And we have if we complete it, we actually have what? A semicircle. Are you seeing that? We actually have a semicircle. We actually have a semicircle, in other words, formed on this straight line. So if you notice that this is a semicircle formed on this straight line PDQ. And we have part of it which is 65, another part being 90. So what's the remaining portion? So remember that rule, adjacent angles on a straight line are supplementary, meaning they add up to what? They add up to 180 degrees. So we could have found the same angle QDC, using the principle of angle on a straight line. Not a circle theorem, but an angle fact indeed. So angle QDC could have said is equal to 180 degrees minus 65 degrees. And then we also could take the 90 degrees away as well. And that would have given us the what? The 25 degrees. And the reason would be what? Adjacent angles on a straight line are supplementary. And the word supplementary means what? Add up to 180 degrees. So I can leave it like this, adjacent angles on a straight line. That's the reason why we add these two angles and subtract from 180. Remember, if you have two negatives, you're going to add and keep the sign. So it's 180 minus what? 155. So minus 65 and minus 90 will give us minus 155. So 180 minus 155 will be 25 degrees. Okay, so let's look at F. Now part F, angle DQC. All right, so now let's look at DQC, angle DQC. So we're going to go from D, identify where Q is, go straight along that line, straight down to Q. And we're going to turn from Q now, we're going to go down to C. Remember, it's DQC. So we're going to go right down here. So we turn, so from D to Q, and we turn at Q, go right down to C. So this is the angle we're looking at. So DQ is this line here, and QC is this line here. So connecting those two lines, we have an angle formed at Q. What angle is this right here? Well, we can actually find angle DQC, which is this angle here, two ways I'm seeing. One, we can identify the fact that angle Q is part of this large triangle, which is triangle ADQ. Go back to A, right? We can identify that fact. So if we look at that, A, D, and Q, we know that this angle here is 25 degrees, correct? This angle here is 25. This angle here, angle ADQ, is a combination of what? So if we were to just look at this angle right here, it is separated into two angles, right? Because we have a C here, right? This part of the angle here is what? This part is 90 degrees. And this part we found to be 25 degrees. So angle D itself, angle ADQ, is 90 plus 25. And that's 115 degrees. So this is 115 degrees. So let's enter that. Now, of course, in your exam, you can actually do this little sketch. And of course, in the exam, you can do this, these sketches. Of course, in your exam, you can do these drawings to assist you. And I'm sure they will look at it and award you marks for these, in case you don't have probably explanation or something, but you show by sketch. Who knows? So this angle that's divided in two parts is a combination of ADC and CDQ, which is 90 plus 25, which is 115 degrees. So this entire angle is 115 degrees. So we have two angles of triangle ADQ already. So we can find this angle here, which is angle DQA, right? Going from D to Q to A. We can find that angle by taking 180 degrees and subtracting 25 degrees and also subtracting the 115 degrees there. Of course, this is the same thing as writing it as 180 degrees subtract the sum of these two guys, 25 degrees plus 115 degrees. All right, you recognize that they're the same thing, because this minus will make this a negative 25 as we have here, and this minus outside will make this 115 also negative 115 as well. So either way of writing it is totally fine. And so this is going to give us what? 25 plus 115 will be how much? All right, so 25 plus 15, that's 40. So that's 140 degrees. All right, so we want to ensure that, okay, so 25 plus 115 is 140 degrees. So what we want to do, we're going to write back the 180 degrees that we did not use as yet, and the sum of 115 and 120 and 25. The sum of 115 and 25, we're going to write it as 140. And when we take 140 from 180, also put the bigger number first, we'll get 40 degrees. So this angle here is actually 40 degrees. If you want to write it inside, it's fine. If you want to write it outside, it's the same thing, that's fine. So that's 40 degrees. So you got full marks for that as well. Oh, we forgot to put a reason. Sum of angles in a triangle. All right, but you want to ensure you're talking about which triangle you're talking about. So you could say considering triangle ADQ. All right, so if you want to make a little note of that when you're doing this one. All right, there could be more space on your paper, so you can say considering triangle. So the symbols means triangle, triangle ADQ. Considering triangle ADQ. Okay, so you can say considering triangle ADQ, which is one you have here. When you take 180, when you have 180 and you take some of the other two angles from it, you get the remaining angle. And so your reason at the end will be sum of angles in a triangle, which is equal to 180 degrees. All right, so we are down to the last question, which is to find angle ABC. So if you look at it going from point or vertex A to vertex B, I'm going to turn off this straight path, which is AB, going straight now to C. So we're going from A to B, and then from B to C. So there's two straight lines. Line AB and line C meet to form angle B. So going from vertex or endpoint A of this straight line AB to its other endpoint B. Now we're going to turn towards vertex C. So this is the angle we're talking about. What angle is this? Well, if you notice that angle ABC, it's a part of the quadrilateral. It's a part of the cyclic quadrilateral. And what do we know about a cyclic quadrilateral? Because this cyclic quadrilateral is a four-sided shape, a four-sided polygon with its what? With its vertices on the circumference. All right? Only two angles for this cyclic quadrilateral we know. We do not know the angle DAB. We only know part of that angle, which is part of the triangle ADC. But we do not know the complete angle here. It's not necessary for us to know it. Neither do we know this angle as well. And it's not necessary for us to know it based on the questions asked. However, we know one of the angles of this cyclic quadrilateral. We know this angle here, which is 90. Now before you say there's another way of finding this, which is just straightforward, I know. But I just want, we already use this principle already to find this one, the same principle to find this one. But I just want to touch on the other circle theorem fact. All right, so we have a four-sided shape, but what do we know about this four-sided shape? This four-sided shape is within a circle and all its four vertices are on the circumference. And what do we know? We know that opposite angles in a cyclic quadrilateral add up to 180. So for instance, angle D plus angle B, so this is angle D here, plus angle B is equal to 180 degrees. What's the reason? Opposite angles of a cyclic quadrilateral are supplementary, which means add up to 180 degrees. So this angle here is 90. So what would this angle here be? Remember, these two angles must add up to what? 180. So if this is 90, that is the reason for this being 90, because both of them are opposite each other. They're facing each other, in other words. They do not share common legs. Okay, so this angle has this leg and this leg, while this angle here has this leg and that leg. They do not share common legs. And so we say that they are what? Facing each other. They are supplementary. And we know that opposite angles of a cyclic quadrilateral, the two angles facing each other, must add up to 180. So if this is 90, then this also must be 90, because 90 plus 90 give you 180. So that's one of the reasons we can state that it's equal to 180 degrees minus the opposite angle to it. In this case, it's equal to 90 degrees. And what is the reason for that? Opposite angles of a cyclic quadrilateral. All right, so angle ABC plus angle ADC is equal to 180. So that's the reason why we did our subtraction there. So that's full mark as well, so another full mark. All right, so hope this lesson was helpful in your revision. And I went about it very slow because I really want you to understand the concept. How to identify the angles. I took my time to ensure you understand where the angles are located and what things you must consider when doing problems like these. Okay, enjoy your evening.